start this up. Okay, so let's see here. I sent out an announcement, didn't hear anything. Fair enough, it was the weekend. Made an executive decision. How about 4 hours today? It's the lesser of two evils. Well, set theory is kind of fun in a way because I just kind of introduce the rules like a board game, and then you have to do all these problems and play around with it to learn it. So I'm really just going to walk you through definitions today. And if you don't have a printout yet, look at me. I even sent it to the printers. And then so today mostly we'll just be working on problems. Like I said, can't remember if it was in my announcement. I was kind of spamming you guys. From 6 to 8, kind of our Friday. We're gonna do Friday from 6 to 8 today instead. But of course, I understand if you have to go, that's totally fine. I've posted the solutions already. You can definitely just take the problems home. Probably been a long day. That's totally fine. I just want to be here for you in case you have questions. Okay. I guess I kind of made notes in 3 different places last night. It's kind of all over the place, I guess. So like you're set there, I'll bring printed copies to class, but you will need extra paper to work on the exercises because I didn't give any space because that would be a lot of printing. I've got some paper if you need it, but, and then for next week, before I forget, I want you to read chapter 2, which is on combinatorics. I'll save that for next week, I guess. Yeah. Any questions before we begin? Yeah. Come on up. There we go. I was starting to feel bad about my printing, but now I feel good. Did anyone have a chance to skim the textbook? Then you'll know that it's quite heavy on a lot of things. So I have tried my very, very best to condense it to all the things that I want you to know. And sometimes I get trapped by all these fun facts that they throw in there. So I do incorporate some of those. But here I am just flat out stealing from the textbook. And I'm not, there are some times where I reword things a little bit, but I'm not reinventing the wheel, but I am kind of kicking out some of the stuff that the fluff that we don't need. But if you do want more detailed explanations, then you can look in the textbook most of the time. Okay, just so you're not completely swindled by my amazing academic writing, I'm stealing it. But there, if I say it, it's okay, right? I think. Oh, definitely. Open source and all. All right. So, set theory. Sets. We have an intuitive understanding of sets, right? A set of Pokemon cards means what? I don't know why I said that. I'm too old for Pokemon cards, but anyways, too old for Pokemon cards? Did you say that right? Yes. you have a set of Pokemon cards means what? You have a collection of Pokemon cards, right? And so intuitively we understand what a set is, and a lot of things in math kind of hinge on sets, okay? And so first term that we're going to talk about is, and I'm gonna try to not highlight my entire document. I'm gonna try really hard, but it's gonna be difficult for me. And this is important, and this, if it's in the document, it's important. And so it's worth reading entirely. But so in a set, we have elements. Okay, so a set is a collection of elements. So they're not necessarily objects, right? But that's kind of where we start. And so what if we, not an object, but what if we think about outcomes, right? So in statistics and next week in combinatorics, we're going to talk about outcomes, okay? So for example, if we flip a coin, what are the outcomes, or what are the possible outcomes? There are only two outcomes. We're ignoring, I know everyone loves to point out the scenario that can happen but rarely happens, where the coin lands on its side, but eventually it will fall to one side. So I'm ignoring that special case. And so we only have two possible outcomes, right? And let's denote them by H and T, heads and tails. Fair enough. Right. So then our elements are H and T. So they're not objects, but they are elements. And usually what we do to denote a set is we close it up in curly brackets. Okay. And so we use curly brackets to denote a set, such as H, T in curly brackets. That's the set of possible outcomes from flipping a coin. My left curly bracket is usually so good, and my right curly bracket is just like a squiggle. Do you guys still have to write like code? Are you writing a lot of curly brackets yet or no? Yeah. How are your curly brackets? Left one's pretty good, right one? Is it like mine? I've had years of practice and I just can't. Talking about sets, we can talk about more than one set, right? Kind of leaning into probability and combinatorics because stats is my jam. What if I flip a coin and roll a die, right? Then I have two possible sets that I could be dealing with, right? The outcome from the coin, the outcome from the die, right? And so usually what we do to keep these little guys straight is we give them names, right? And so that's we're no strangers to that. Some kind of you don't have to use a capital letter, but you should. So we just always use a capital letter. Sometimes in rare instances, if it makes more sense to use some other symbol, then fine. But we usually name sets with capital letters, and we usually start at the beginning of the alphabet. But that's just me being picky, I think. And so generically, we're going to be talking about a set A, and then if I introduce another set, it'll be set B. If I introduce another set, it'll be C, or I'm getting ahead of myself. Fine, I will get ahead of myself, right? There are scenarios where there are kind of logical choices for names of a set, right? For example, if you have the set of binary digits, right, 0, 1, then you might call that B, and the decimal digits 0 through 9, then you might call that D, for example, just to show which ones are which. But first, little itty bit of notation. So if X is an element of A, then we're going to use X. And how can I? X is in the set A. So in the set. And then, of course, if X is not an element in A, then we use not in the set. It's like an E looking thing, and then not has a slash through it. For example, if we name the set here that we introduced, right, we're flipping a coin, so I'm going to call it C for coin toss, maybe. I don't know. There are only two elements in the set, H and T. Okay? And so we might say, is H in the set C? Yes, it is. Right, H is one of those two elements. What about, is 1 in the set C? It's not. No. Therefore, 1 is not in the set C. The thing about set theory is none of it's difficult. It's just kind of forcing you to think about things that you probably haven't really paid attention to in the past, probably. For example, so ellipses. So an ellipses is when you have dot, dot, dot. Okay. So 3 consecutive dots, and there are lots of ways we can use an ellipses. Okay. Here are 3 different cases, right? And I think you can all look at these 3 cases and say, okay, I think I understand what all those sets mean, right? But can you articulate what the ellipsis is doing in each scenario and why they're different? That's difficult, right? It's things we don't really need to articulate very often. In the first case, right, we understand that, okay, the set G has elements 1, 2, all the way through to 100, right? Going up by 1 as kind of the pattern continues, right? And so here, these ellipses here say, okay, it should be obvious at this point what the rest of these numbers are, so I'm not going to list them, but I do need to tell you where they stop. Right? And so here, in this case, it is clear what elements are included but not listed. Fair enough. One, two, three, dot, 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 ellipses. In this case, right, we understand that that means, okay, then that list goes on indefinitely, right? Which is a different meaning, right? Slightly. They're all similar, right? It keeps going forever until 100, right? If there's no end, then the list goes on indefinitely. The third one, right, is very similar to the first one, but now we're going to some unspecified point, right? And so here, n could just be 1, right? And so then these ellipses don't do anything, right? It can just be a set of 1, right? It's allowing for any number of objects up until n. So I'll just write out what I have, even though it's kind of long. If we want to list a more general set, I'll start there. A more general set from 1 to n. I'll make a note here. Note n could be 1. So then the set would just be 1. That's allowed. So even though it's allowing for space, and usually we would have space, right? But it's just a general set. Couple of common sets that we use relatively frequently, some more than others. Notice how they're all kind of bolded math style. So here, all I do is I kind of put, so if I have to draw these, I add a back to one of the parts of the letter, like that. Okay. Usually you don't have to, oh, they changed the setting. Okay, so the set P is the set of positive integers. While integers aren't introduced until here, right? But Z is the set of integers. Now integers are any whole numbers from negative infinity to positive infinity, right? And so then the positive integers would be 1, 2, 3, dot, 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 ellipsis. The natural numbers, slightly different, include 0. Okay, it's kind of a hot debate in discrete mathematics. Is this the set of natural numbers? Well, I even added the footnote. This is where they roped me in with that kind of fun fact footnote. So some people, roughly half the world call the set 1, 2, 3 the natural numbers. We don't. We call 0, 1, 2, 3, etc. the natural numbers, which I guess is the Pythonic approach. But they're both right. But for us, if I say natural numbers, it includes 0. Right? And so we'll specify the positive integers. Right? I'll highlight. Technically both right, but in this room, only one's right. Otherwise, what a mess. So we talked about the integers. Q is the set of rational numbers. What's a rational number? It's a fraction, right? Meaning that I can rewrite a number as a fraction, right? 1.5, for example, I can rewrite as a clean fraction. Irrational numbers, I cannot. They're not on here. That's okay. Not common. The set of real numbers is very common. This is any number from negative infinity to positive infinity. Right? Any number on a number line is in the set of real numbers. Any number on a number line. I guess I could call it the number line. Oops. And then complex numbers, right? We're not going to deal with complex numbers, but you might have seen complex numbers in the past. Maybe. Decimals, depending on if you can rewrite them as a fraction, they would all be in the real numbers. So even pi is a real number. It's an irrational number, but kind of goes from into, they all get lumped into the real numbers. And so we're going to talk about the set of real numbers quite often. So it's worth hanging on to. Oh, and I also, of course, I shouldn't say of course, I do assume that you are comfortable with the integers, right? That when I say integers, you say, yeah, any whole number, negative infinity, positive infinity. Okay. Questions so far? Terminology. How about some more? Have you used set builder notation before? Looks like this. Okay. So what we can do, describing elements in a set can be quite tedious. And so it's often really nice if we're able to kind of condense it and summarize it in a nice clean way. And so one of those ways that we can do that is set builder notation. And so set builder notation looks something like this, where the set of rational numbers, Q, right? We already said, okay, rational numbers are fractions. Well, the set Q can be summarized as any number A over B, so generically A over B, such that, so this you're going to read such that, so this vertical bar, right? And so here, this is the general form of any element in the set of rational numbers. And then here's the criteria. And so here, this is the general form. And then, oh, maybe I'll use a different color here. And this is kind of followed by the criteria. the criteria, if we had to read this, we have all the, if we take our time and break this down, we can read this, right? I introduced the such that, but the set of rational numbers is the set of elements A over B such that, okay, A and B are in the set, of integers and B is not equal to 0. Whew. I mean, pretty impressive that we can condense that all into that little notation, right? But it kind of goes on in the textbook to say, okay, if you're not comfortable with this notation, you're welcome to write it out, but eventually you're going to get really frustrated writing out all those words, and you're going to start adopting kind of shorthand, and that's what this notation is. So it's supposed to help you. It is difficult in the beginning, right? But the more you read and kind of take it nice and slow, then you'll get better over time. Okay. I'm wondering, should I write out what this says in words? Should we do that? Let's do it. Okay. This is going to be read as the set of rational numbers Q is the set of elements A over B such that A and B are in the set of integers Z and B is not equal to 0. Oops. Oof. That's what that says. And that's how you would read it. One thing that I haven't mentioned yet is that commas you read as and. So that's why it's A and B are in the set of integers and B is not equal to 0. Okay. Any questions about subfolder notation? Okay. So I do want to make a note here. There are many kind of correct ways of writing out a set. There are many correct ways of writing a set. For example, just as an example, if I say X is in the set of real numbers, I can do that. I tend to put my criteria after the such that, but it's allowed to go before. Such that, and then my criteria is x squared minus 5x plus 6 equals 0. If you factor this, then this is the set of, 2, 3. If x is 2, that's true. If x is 3, it's true. Versus I can do the same thing, x. So the set x such that x is in the set of real numbers and x squared minus 5x plus 6 is equal to 0. This is also the set of 2, 3. I like to have all my criteria on the one side, but sometimes it's just a little cleaner to move it on the other side. These are both equally correct. So we have to be a little bit flexible, right? But the more that we see and use and write, right, the more flexible we'll become. So what I want to do, I've included a lot of exercises, and just to make sure that we kind of don't run out of time with me blabbing too much, I'm just going to circle these, all of them, for you to do later. Okay. You can glance at them now, right? Kind of give it a go, but we'll, I've posted the solutions already, right? So to most of these, some of them I sprinkled in afterwards, so I don't have those solutions made up yet, but I'll post those. But so what I want to do with my time is just talk you through all these definitions and things and concepts. Okay? But at this point, right, you have all the tools to do all those problems, something to look forward to. Okay. A finite set, if I say I have a finite set, you know what that means. What does it mean? It means that there's some finite, I'm trying to not use the word finite, but there's some finite number of elements, obviously. Okay, so we know that one's easy. Okay. Now, there are infinite sets, but we're going to focus on finite sets for now. Okay. And so in finite sets, we're going to talk about the cardinality, which is the number of different elements. I guess I'll finish. It's called its cardinality. Okay. So we're going to talk about the cardinality of a set, so the number of elements in a set. Because it's finite, we can count them, so that's nice. We denote it with these vertical bars around a set name. Context will tell you that this is not the absolute value, right? And so it looks the same, right? But it will be clear from context that it is not the absolute value. Should have given myself a little space there, I guess. But it looks the same, right? But if it's around a set name, then you were talking about the cardinality. I think on the assignment questions, We can also, or denoted by a lowercase, where can I put this? By n of A. N meaning the sample size, right? Or the size of A. So it could be a lowercase n of A, but that is the cardinality of A. I didn't really spend much time besides giving myself some spaces, but clearly not where I needed them, where I would think of things. But I should have made things a little bit more lofty here, but that's okay. First pass. So I'm gonna be working with the cardinality. What about subsets? You understand subsets? In fact, we've already seen subsets, right? We talked about the set of positive integers, but that was a subset of the natural numbers, which is a subset of the integers, right? If we go back to these kind of named sets, right? What do we mean by a subset? P is a subset of n because I can take all of P and stuff it into n, right? I can take all of the integers and stuff it into a rational function, but Emily, it's not a fraction. What if I divide by 1? Huh? Clever. Clever girl. How about real numbers? Well, fractions, I can stuff those into. So these are all just, what are those dolls? Russian dolls, right? They're just subsets. They should rename the show, which I think about way too often. That show, it was pretty weird. So we know what a subset is. Do we know the notation yet? A is a subset of B. Is a subset. And the ordering of the elements is unimportant. Yeah? And so you could have 1, 2, 3 and another set of 5, 4, 3, 2, 1. The first set is a subset of the second set. Bless you. I'll just have my example. We saw earlier that the set of positive integers is a subset of the set of natural numbers, which is a subset of the set of integers, which is a subset, what was the next one, of Q, which is a subset of the set of real numbers. And then I'm gonna drop the complex numbers because we don't use them here. So we can just stuff sets, right, into other sets, making subsets. If I say A equals B, right, we know that a capital A and a capital B denote sets now, right? And so then what if I tell you that they're equal to each other? then you would check in and say, I wonder, that must mean that they have the same elements, right? Otherwise, how could they be equal, right? And that's exactly it. So if and only if every element, and I'm going to introduce, we're not going to be writing a ton because I'm trying to avoid it, but if and only if is abbreviated IFF. Might come in handy, I don't know. And so every element of A is an element of B. And conversely, every element of B is an element of A, which is really just to say that A is a subset of B and B is a subset of A. Huh. So many things that you already know. Cool. Maybe just never thought to say them out loud. What about the empty set? The empty set, you may or may not be familiar with the empty set, but the empty set is a set that contains no elements. Okay? And it's denoted by this 0 with a slash through it. Okay. It is still a set though. It's just the set of no elements. And so this is where I want to make a note too. If you're the type of person who likes to draw their zeros with a slash through it, can't do that anymore. Although it is good. I think it's a nice way to indicate that it's a 0 and not an O, but now it means something. It means the empty set, which is completely different from 0. All right. We can also call it the null set, but I tend to call it the empty set. Okay. Usually I don't have this kind of, it feels a little backhanded. It's clear, we hope, from the definition of a subset, blah, 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 blah. I don't like to include that, but I was getting a little lazy and I didn't feel like rewording it. So I just stuck it in there. It is clear, we hope. Math textbooks, they're always like that. It should be obvious to the reader. It's absolutely not. But what should be clear? If we have a set A, then A can be a subset of A, right? All the elements of A can fit into A, that's fair. And also, the null set is a subset of A, subset, right? So this is where we need to kind of pay a little bit more attention. It's not an element of A necessarily, right? But it is a subset of A, is no numbers, right? So here, if A is a non-empty set, okay, then when I take A as a subset of A, we call it an improper subset of A, whereas all other subsets of A, right, including the empty set, are called proper subsets. We don't really care about that. It's just good to have that terminology of improper subsets. So if I take the entire thing of A as my subset, then that's an improper subset because you didn't do anything, right? Whereas if you take just a portion of A as your subset, then that's called a proper subset. Even if you take no elements from A, so the empty set, then that would still be a proper subset. what's funny then is the empty set is an improper subset of itself. What? That's just a fun fact. You don't have to worry about that one. Oh, and where was I here? Questions so far? So again, I'll parking lot these. First one's true, false. Let's think about this one. Only because I snuck it in there because I was thought, oh, that's kind of a fun one. So why is there no set A that satisfies that A is the set of 2 and the cardinality of A? Well, what's the cardinality of A? In this case, it has 2 elements, so the cardinality would be 2. But if I have multiple entries, multiple elements of the same number, I only write it once. So it only really takes the space one time. And so then I get 2 and 2. But then the cardinality is just 1, and that can't be. Kind of fun. So I talked you through it. I'll still write it out in the solutions, but just something to think about. Okay. Questions? Yeah.
Set of 1 and 2 and the cardinality of A, that would make sense.
Then that can happen, yeah. Yeah. Because then 1, 2, 3, and the cardinality. I think so. I'd have to kind of think on it a little bit. Yes, I think so. Proofs. Good question. All right. Would it work? Yeah. The intersection of 2 sets is, I don't know, not as intuitive as the other things that we talked about, right? But if I tell you, okay, if I have, it's going to be really hard. We don't introduce Venn diagrams until later on this page, but or maybe even, yeah, maybe later on this page. But usually we visualize sets with Venn diagrams, right? So Venn diagrams are just a visualization of sets. And so if I talk about a set A and a set B, and then I overlap them where there's overlap, right? Then that would be considered the intersection. Okay? And so for now, so I'll draw it visually. There's a huge space here where we're going to draw some Venn diagrams and visualize these things. So let's just talk about what they are. Okay, so I've got 2 sets, A and B. The intersection of A and B is denoted by A and then upside down U, B. Okay. It's read as the intersection, okay, but I read it as and. Okay. And so this can be read as and then how I remember is I take my intersection and I just kind of make it an A, and then that's my reminder to myself that, okay, that's and. Okay? Has to be in both A and B in order to be in that set of A and B, the intersection of A and B. So now the intersection is a subset, right? And it's the set of all elements that are in both A and B. It's not too far-fetched, my and, but technically you should read it as the intersection of A and B, but just read it as A and B and it's easier. And so what we can do, are we ready? The colon is the same as the vertical bar, and just kind of getting used to different ways of showing the same thing. Okay, but A and B, there you go, is the set of X such that X is an element of A and X is an element of B. As an example, if we let A be the set of 1, 3, 8, why not? And B can be the set of -9, 22, and 3, then if I have to look at the intersection here, I've got overlap. Both of them have a 3. So then the intersection of A and B is the set of 3. Just one element, 3. Nice. Easy enough. If we take it a step further, what if we're solving a system of equations, which we will be doing in, I want to say chapter 5, we'll be solving some systems of equations. Maybe not this, but what if we have x plus y is 7 and x minus y is 3, right? So then if I let A be the set xy, right? So a coordinate where x plus y is 7 and x and y are in the set of real numbers. So that's how we usually toss that in the, and it says in the real numbers, right? Meaning any number, it can be any number, you know? Just not a complex number. And the set B, which is also a coordinate, right? We're gonna force these to be the same coordinate, right? To find the intersection, right? And the intersection is just that, right? If we think about 2 lines, it's the easiest thing to think about. Then we're gonna be looking for the same coordinate here, x minus y is equal to 3. These 2 things, if we solved them, we would find that they intersect at when x is 5 and y is 2. Okay. Could draw those in Desmos to see. Let's do that. Why not? It'll load. I think it was x plus y is equal to 7. Makes a line, just like we thought. How about x minus y is equal to 3, I think. Made 2 lines, so those equations, 2 lines. The intersection is at 5, 2. And so that is the intersection, just one element or one coordinate in that set. Let's see if I can put these in one screenshot. I'll just bring it in. Done. My camera roll on here is not very spicy. Let's see here. Oh, crop. I'll just keep a little tiny version of it, just so you can remember. Oh. the set of integers and the set of rational numbers. Well, we said, okay, all of these are subsets. And so, of course, the set of integers, I can't expand it past the set of integers, but I can rewrite them all as fractions, right? 3 divided by 1 is a fraction. It's pretty boring, right? But it is an integer and it is a fraction. And so then the intersection is just the set of integers. Can also have where the intersection is the empty set, right? And so we got 3, 5, 9 and negative 5, 8. And then the intersection is the empty set, meaning there are no elements in that intersection. That's allowed, that's fine. The name, if there are no elements, we say that A and B are disjoint sets. So visually, there's no elements in common, right? And so A and B are disjoint if the intersection of the two is the empty set. So that's the intersection. We can also talk about the union. The union, right? We kind of, it's a little bit more of a stretch. I don't find that it's quite, as natural as the other things again, but the intersection, okay, we kind of got there, right? Whereas the union is kind of everyone in both the sets are kind of married in a union. I don't know. Let A and B be sets. The union of A and B is denoted by A union B, which is kind of easy, I guess. But U is for union, but I can be read as or. So whenever I see that U, which is the union, but it doesn't really tell me what to think about, right? The union. But if I say or, so A or B, then it's all those elements that are in either A or B or both. Okay, that part throws people off sometimes, but it's allowed to be in both. Okay, so I'll highlight that there, or I'll underline it at least, right? Because that can cause some confusion, right? But it's allowed to be in both. If the set A is 2, 5, 8 and B is 7, 5, 22, well, then I take the elements of A and I smush them together with the elements of B. And then usually what we do is we remove any duplicates, right? And so 5 is in there twice, right? But we only list it once. Only listed once. And that's proper. You don't want to have extra elements in there bogging you down. 5 is a 5. It's either in the set or it's not, and so being in there twice doesn't mean anything. In kind of way upper level math, right, it would mean something, but not for us, not in this course. Okay. What about the set of integers and the set of rational numbers? Or I guess I should say or, right? The integers or the rational numbers, but I can just summarize that as the set of rational numbers. So that's cool. How about A or the empty set? Well, that's just going to be A. Empty set's allowed to be in there, but there's no elements in the empty set. And so it's just always going to be A, right? Because The empty set is not contributing anything. It's just hanging out.
Order doesn't matter, right?
Order does not matter.
So if it's A, U, B equals to B.
That's right.
they're the same.
Totally. In fact, I think it's a couple pages out, but we've got all these laws saying that they're the same. Okay. I'll add to my note actually, only listed once. And I know you meant a different order, but I do want to talk about this order as well. So only listed once and order does not matter in the set, but also in the union, nor the intersection. So we're gonna have a universe or a universal set. Okay. The universal set is the set of all elements that could be in a set. Okay, so that are allowed to be in a set, whether they're included or excluded, right? Depends on what the rule is that we're talking about, but and so we're going to use the capital letter U is reserved for the universal set, so you don't want to use U. But I think we're ready for Venn diagrams. And I should have saved a joke. Usually Venn diagrams are really good for jokes, right? A Venn diagram, the anatomy of a Venn diagram. We start with a rectangle. Right? The rectangle represents the universal set. Right? So here, the rectangle denotes the universal set. Okay. It's probably in here. Okay, I'm not gonna write it. I see that I have it here. There's no original thoughts, I guess. Although I thought that one was, but just so I have more room to draw more Venn diagrams. So here we've got the universal set U. And then let's say I have some set A is a subset of the universal set, right? That's how I would denote that. I can have the set B. This is a generic Venn diagram. This is just for visualizing. So you try to make your circles just the same size. I'm not very good at it, even though I should be. As I draw these all the time. The size of the circles doesn't mean anything. You want to make sure that there's overlap, even if the two sets are disjoint. Disjoint meaning there's no elements in common, right? And so they share an empty set. And so this is just a visualization. So I'll highlight it here because it snuck up conveniently here. So the region representing A and B, which must be where? Must be there, right? The intersection, A and B, all the elements that are in both sets. Okay, and so here this is a visual representation of A and B, the intersection. So when we draw it, it doesn't look like an empty set, but it could turn out that it is an empty set, and that's totally fine. You don't have to change your diagram or anything. Right? What if we do the same thing? What if we have to draw the union of A or B? Oops. It was all the elements in A, right? Here are all the elements in A, or all the elements in B, or both. Sorry, say. All this. Perfect. Perfect, perfect. Well, I guess I could do something fun, like use the highlighter or something. I don't know. It gets tricky. Made my A and B disappear. Oh well, whatever. This is A or B. I think for one of the questions that I have on here, but also on the assignment and on the test, because it's a more fun question, we're gonna have not 2 sets, but 3 sets. So I should probably show you what that would look like, even though you might. That's usually where the jokes are. Right, you've got some set A, some set B, and what color haven't I used? Purple. And some set C. You want to make sure that there is an area where all 3 overlap. This would be the intersection of A and B and C. That's allowed. We can keep tacking them on. I'll never make you do 4 because it gets a little bit weird. But 3 is perfectly reasonable. And I forgot my U, but you don't have to write the U, but we're just starting, so I should probably start writing these. All right. So a lot of the time, how we use these Venn diagrams is, yes, to visualize sets and to visualize kind of their relationships, but usually what we're interested in is the cardinality. Okay? And so what we're gonna do is we're gonna use, this one's the cleanest, so I'll talk about this one. We're gonna use this Venn diagram to talk about how many, I don't know, people are in A, or how many elements, sounds boring, but how many elements are in A or C, right? So we can use the Venn diagram to visualize it. And so now we're talking about how many elements, that's the cardinality, right? And so what we're gonna do is we're gonna be really careful, and we're always gonna start in the very center and write down, because these questions, and I really hope I have one coming up soon. Do I? Okay, maybe not so soon. It's on the next page. But I give you the number inside the overlap. Okay. And then you have to subtract that number. And what I want you to do is just imagine it being just one flat surface, right? Instead of 3 rings piled on top of each other, you're gonna take away the number in the overlap, right? And so, for example, let's do an example. We can give the cardinalities of each space. So it might look something like this. I didn't give myself very much room here. Okay. So if I've got A, B, and C, if I tell you that the cardinality of this space here is 5, I'm just gonna put numbers down that I think can work. More like that I could maybe do the math on. Right? So now I've filled in all the spaces, all the puzzle pieces of the overlaps, but I can also have something that's only in A. Let's say there's 10 here and 12 in B, only in B. And can I do math? 15 in C. And hopefully I haven't overshot it. Oh no, I'm safe. Let's say there's 50 here. How do we read this? Well, first, what's the cardinality of A? Cardinality of A is the number of elements that are in all of A, right? And so this 10 here is just this kind of half moon area, right? So 10 plus 1 plus 5 plus 2 are all the elements that are in A, right? They're in A and also overlapping with some other set. That's okay, but they're still in A, right? And so can I do this math? 7, 8, 10, 18. Right? Because I have 10 plus 2 plus 5 plus 1. What about the cardinality of A or B? Huh? Crazy. A or B. So they're allowed to be in just A or this little guy's in A or B, which includes these guys as well. So the set from A, so the 18 from A plus 5 plus 12, whatever that is. 18 plus 5 plus 12, 20, 35. So usually that's how we use the Venn diagram, is to figure out how many elements satisfy some criteria. But the question usually makes you fill in these areas first. Okay? Let's just briefly, I just want to, because I keep talking about it, but might be something like this. So we've got D, M, and G, which is, so We have all students at a university. D means day students. M means that they're math majors. And G means that they're graduate students. And so we're not going to do it, but I want you to see what the question looks like. So I give you the size of the universal set, right? Which would be what? That has to be the total count of all the spaces, right? So in this case, the total count has to be 16,000 in this example. The total number of daytime students is 9,000. The total number of math majors is 300. And the total number of grad students is 1,000. Okay. It's not very helpful because we know that there's overlap. You're allowed to be a daytime grad student math person. That's allowed, right? Or some combination. And so then we're given more information. So also assume that the number of day students who are math majors is 250. Okay. So you know that the total of that overlap has to be 250, but then 50 of whom are also grad students. Okay. That's going to be the very core, right, of all the overlaps. And then you're going to subtract that core because you've already written it down from the 250 as you move out, right? And so if you've already taken a number into account in your Venn diagram, which is how I recommend that you solve these because it's hard to think about, then you subtract it from any future kind of additions. Okay? And then you're given all this other information. Okay? So 3 sets. So you've got the 3 circles, right? But always start in the very, very center and figure out what that number is. And then you can kind of bloom out. Okay. Okay. Oh, I guess I'll keep, oh, whoops. I'll highlight this because it's a continuation of this, but so an area might not look empty, but remember it's just a visualization, so it's allowed to be empty and that's okay. What about the complement of a set? The complement of a set is the opposite of that set, right? It's all the elements that are not in A, for example. Okay, so the complement of A relative to B, and usually we do it relative to the universal set, but relative to B would be B minus A, right? You just take away all of anything that's in A, you just take it out. Okay. And so B minus A is going to be the set of x's such that x is in B and x is not in A. If U is the universal set, then U minus A is denoted by the complement of A. So we've got this kind of common notation of A superscript C for the complement. Okay. But that's if you're taking it from the universal set, which is usually what we're doing. And confusingly, if you've done any calculus, in upper level stats, we use the prime notation. So A prime is the complement, but that is also the derivative, which we also use. Oh, what a mess. Anyways. Okay. The complement. So now we can, let's see here. How cool is this? For when I get lazy. The complement, if you had to visualize it, here I've got the universal set. And here I've got A. Let's start little, right? then this, anything that's not in A is the complement of A. Complement of A. Okay. What about leveling up? AB. So now I'm going to take A minus B. Oh, sorry. B minus A. I was reading it in the wrong order. B minus A. So from all of B, I'm going to take away anything that's in A. And what does that look like? Looks like this. Right? Excluding anything that's in A. So we're going to use Venn diagrams to kind of illustrate a lot of these concepts. And if they don't help you, then that's sorry, if you don't need them, then that's cool. You don't need to use them. But I encourage you to kind of get comfortable using them. The symmetric difference is probably the kind of the hardest one that we're going to talk about today, but okay, I take that back. But let A and B be sets again. The symmetric difference of A and B, which is denoted by this circle with a plus in it. Symmetric difference is for some reason denoted by a circle with a plus. I can't explain it. I don't know why. It's the set of all elements that are in A and B, but not both. Okay. And so I guess this should actually be, we're using and loosely. I would probably replace that with or, so A or B, but not both. Okay. But we see it here. When we talk about the symmetric difference of A and B, it's the union of A or B minus the intersection. That one's a little finicky, right? But visually, what's that going to look like? A, B, oops. So I start with the union, which is anything in A or B, and then I subtract the intersection, and I'm left with everything that's just not in the intersection. Right, this is the symmetric difference of A and B. That's what that looks like. So if I talk about the same set, so 1, 3, 8, and or I guess they're new, 2, 4, 8, then the symmetric difference is I have to remove any overlap, right? I've got an overlap of 8 in both sets. So then 1, 2, 3, 4, listing all the elements that are not in both. The symmetric difference of A and the empty set is going to be A, because if I take away the empty set from A, I'm still left with A. But also the symmetric difference of A with A, if I take away any overlap in A with A, I'm left with nothing, no elements, and so then I get the empty set. Taking away the real number, or from the real numbers, the set of rational numbers, I'm left with the set of irrational numbers. Numbers that cannot be summarized as a fraction, right? Pi, E, those guys. Some common irrational numbers. What am I doing? Okay, wow. just swell. I'll let you work on these once I'm done blabbing. Now this kind of printed weird. Can go ahead and add lines if you find that it's helpful. But here is, and just as a note, these laws are from section 4.2, but we're not doing chapter 4. And so this is all I'm gonna grab from there, and this is kind of a logical place to put it. And so not doing chapter 4. But you do need to see these laws, and so here we go. So these laws are some of the laws are obvious, like A or B is the same as B or A, right? On the flip side, you have the same thing but for and, right? A and B is the same as B and A. And so then you don't need to remember the names of the laws. So you can call them by their number. Okay. On the test, I'm not going to make you use it. It's more of kind of just getting used to working with laws as we gear up towards logic in chapter 3. Okay, so it's kind of a warm up for logic, where we will be testing you on it. Yeah. But here, this is just kind of good to know laws, stretch our proof muscles a little bit. So the associative laws say that, okay, A or B or C is the same thing. I can regroup them and say, okay, that's the same thing as A or B or C, right? And so I can regroup them. Same thing with the ands. Distributive laws. Notice how it looks like the and is multiplication and the or is addition. And so you can kind of replace those, kind of. We can think of, oops, as multiplication and or as addition. But that might make it helpful. Then we know those laws. Some of these I think are relatively obvious until we get to De Morgan's laws. De Morgan's laws are going to come back up in chapter 3, but and actually in chapter 2. So we're going to see a lot of De Morgan's laws. But De Morgan's laws says that if you take the complement, so notice the complement is on the outside, okay, of A or B, then when you distribute that complement, what happens to the or? It turns into an and, right? And so by distributing the complement, and it works in the opposite direction as well, you have to flip the sign, okay? So here, kind of distributing these flips that sign, flips that frown upside down, but it's a smile to a frown instead. Okay. A lot of these we can kind of prove with a Venn diagram. You can move through the phases. And so I'll let you do that. This one is tricky. Not something I can test you on because I'm not going to give you this table of all the laws, which I would do if I was testing you on it. And so it's just to get used to proofs which are coming. Okay. And so I want you to think about how you would prove these and which laws are you using, and just make note of which law number it is you're using along the way. Okay. Any questions?
So all lecture will be Monday and Friday altogether. Or we're just doing it.
Yeah. I know. How am I doing?
So if we
I'm
do-
running out of time.
do Monday for one lecture, we would do the targets together.
Yeah.
But we're not doing it.
Well, you'll have time to work on it, ask me questions, hang out if you want. Same as Friday, but I just don't have to wait until Friday to do it. Same as Friday. Cartesian product. Okay, that means nothing to me. At least kind of with my, well, it means something to me because I know what it is. But when I think about kind of what could it possibly be, there are no clues to me here. So we have to rely on the definition. A and B are sets, fair enough. Okay, I'm with you. The Cartesian product of A and B, which is denoted by A times B with the X, okay, has to be the X, is defined as the coordinates AB such that, so now I have these coordinates, right? XY coordinates or AB coordinates, such that A is in the set of A and B is in the set of B. Still kind of hard to see, but what does that mean? It means it's going to be all the possible ordered pairs where the elements of A are the first element and the elements of B are the second element. Okay. And so let's look at if A is 1, 2, 3 and B is 4, 5, right? Then I have to list, so the Cartesian product tells me, okay, A times B is the list of elements or ordered pairs where I've exhausted all the combinations of A and B in that order. So 1, 4, 1, 5, okay, those two are there. Moving on to the next one, 2, 4, 2, 5, phew, they're both there. 3, 4, 3, 5, both there. That's the Cartesian product. One kind of fun thing to note is that the cardinality of the Cartesian product of A and B is 6 in this case. And that is because it's the cardinality of A times the cardinality of B. That's a nice shortcut to check to make sure that you have all the ordered pairs that you should have. That's pretty good.
Let's do that with formula A times B equals something 6.
It's just that, so for us, we accept it as fact that the cardinality of A times B is the cardinality of A times the cardinality of B, which in this case is the cardinality of A is 1, 2, 3 times the cardinality of B, which is 1, 2. which is 6. If you think about a matrix, right, where you have to do all the possible combinations, where the first element is maybe the rows, and the second element is in the columns, right? Then you would have the number of rows times the number of columns as your total number of elements. Right, something like that. All right. Can even do the Cartesian product of A times A. 1 goes to 1, 1 goes to 2, 1 goes to 3. 2 goes to 1, 2 goes to 2, 2 goes to 3, and so on and so forth. And so cardinality should be 9. And so you just want to make sure that you've listed all 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Phew. That's mostly how I use that cardinality rule, right? Just to double check that I listed them all. We can do a Cartesian product of 3 or more sets by the same logic, where A comes from A, B comes from B, and C comes from C. But boy, what a mess. So no thanks. And all right. Let me just see here. Okay. The power set, again, just like the Cartesian product, I don't find that there are any clues in the term power set, but the power set, so we rely on the definition. If A is any set, then the power set of A is the set of all subsets of A. Okay, and it's denoted by this fancy P of A. So it's the power set of A.
It's a combination.
So it's a set of all possible subsets of A. At the most extreme would be the empty set. Okay. And then on the other extreme would be A, right? Both of those are subsets of A, but then I could also have, so in this case here, let's see here. I'll let you look at those, but this one is kind of most helpful. So the power set of the set of just 1, 2 would be the set of the empty set, the set of 1, which is a subset, the set of 2, and the set of 1, 2. Okay, and so it's important to notice that we've got, this is a set of sets. Yeah.
So the power of 5 will be 0 and 5.
Yeah, if you have something like this, well, I guess if you start with the empty set, then it's just going to be the set of the empty set, which is different from the empty set. Oh. The set of the empty set is not equal to the empty set because it has a thing and it's called the empty set. Gets a little boggy.
So what I'm confused is, it always included empty sets on combinations.
Yeah.
So on the bottom of 1 and 2, why is not the combination of 0, 1, 0, 2? 0, 1,
Oh, because the empty set is not in the original set in this case. If it was, then yes. But the empty set is always a subset of the set. Right, from this, let's call it a bag of 1, 2, I could pull nothing, right? And that is a subset of the set, which is my bag. Okay. Got more. Notice here, you're doing the Cartesian product. And at the very last step, you're doing the Cartesian product with the power set. Whoa, yikes. Don't worry, B is very little. Last thing I want to talk about, which is why I had to look ahead, because I almost said that about the power sets. The last thing I want to talk about is sums. Okay. Summation notation might be familiar. And so a sum of numbers like A1 plus A2 plus A3 plus A4 is called a series. And sometimes we zip those up in using summation notation. Fun to do, fun to say. And we write that as A subscript K is the thing that we're summing. And we're summing from K equals 1 to 4 in this case. And so here, right, that is the sum of A1 plus A2 plus A3 plus A4. Generically, so this is all trying not to highlight too much. This is called summation notation. So if we have an expression like this, A1 plus A2 plus A3, all the way up to AN, okay, then we can summarize that in a similar way as the sum. So this is read as the sum from K equals 1 to N of A subscript K. I guess that's how you read the whole thing. So you start and let K be 1, and then you say A1 plus A2 plus A3 plus all the way up to AN. Sometimes we have a place to stop there, and that's nice because then we can evaluate it potentially. But often it just keeps going to some unknown value, N. Some terminology. K is referred to as the index. Usually we use I instead of K, but we can be flexible, right? So whatever is in this spot here is the index, or the index of summation. A subscript K is what we call the general term, so the kind of the thing that we're adding up. We have some initial index and a terminal index, and then we add up the things in between. Some examples. Here we use an index of I, that's fine, right? From I, so the sum from I equals 1 to 4 of A subscript I is A1 plus A2 plus A3 plus A4, right? So it doesn't matter if we use I or K or A or whatever. Well, A would be weird in this case because I'm using it somewhere else. N is usually makes an appearance. The sum from K equals 0, so we can set kind of our, what's it called? Initial index to any number, 0, -2. So from I equals -2 to 2 of C subscript I would look like this. C -2 plus C subscript -1 plus C0 plus C1 plus C2. Sometimes we luck out and we're able to replace these indices with numbers, and then we can actually evaluate the term. And so the sum from I equals 1 to 4 of I squared is 1 squared plus 2 squared plus 3 squared plus 4 squared, which we can evaluate to be 30. Can even get up a notch and say, okay, well, what about the sum from I equals 1 to 5 of 2I minus 1? So then at each step, right, you would replace I with 1, then 2, then 3, then 4, then 5, which you can then evaluate and find that that sum should be 25. We can do this with, or this idea, we can generalize it to any mathematical operation. The intersection, right? We can summarize A1 and A2 and A3 and A4 as just the intersection from I equals 1 to 4 of AI. Same thing with the union. The Cartesian product, uh-oh. I'm blanking on what it's called. It's probably an indication of how important it is. Not very. It's too hard. What is it called? The circle with the something summation. Symmetric difference. Well, not even close. That's okay. So then you can do all these, making a note that a capital pi is the product of numbers. And so then you're multiplying numbers instead of adding them. But it works the same way. You did it. I did it. Sort of. So as promised, give you time to work on those problems here and now, or I'll be around during the week if you have questions. The solutions to most of them are posted. I'll have to fill in some of the ones that I added. But anyway, you want to work through those. Friday starts, I guess, in 10 minutes. You can have a break or do whatever you want. You're all adults. Make your own decisions. All right, but we did it. And I will not see you on Friday. Deal?